So lastly is we're gonna do an extension of this methodology, and we're gonna have model here that has not just two compartments. This model is gonna have 4 compartments. Okay, so we're gonna say the terminology is very consistent, very similar. So S here denotes the susceptible. These are individuals that are not infected. Okay, I denotes individuals that are infectious. Infectious, that means that they are capable of passing the infection, okay, passing on. Also, we're gonna have here a compartment called R, which is the state that individuals go to after they kick off the infection, after the immune system is able to control that infection and they are no longer passing on infection. This state, we can call them recovered. These are recovered individuals. Now you may wonder, what is this state called E? Well, this is for a scenario in which individuals are infected, yet they are not infectious. So this is a scenario in which individuals that are infected undergo a latency period or undergo some period of incubation. Okay, so sometimes this is denoted with the letter E because it's to denote exposure. So these individuals are called exposed. Okay, this means they are undergoing latency, and that has to do with some type of incubation, right? So they carry the pathogen, however, they are not capable of producing gains for infections, yet they're not capable of passing on this pathogen, okay? The rationale here is very similar as to the expressions we wrote before. The main epidemiological process, the main process of transmission of infection here, has to do with this term, which denotes the contacts between those individuals that are not infected and individuals that are passing on the infection, right? So this is a term beta times S times I over N. And then transitions out of I are still denoted in this form, a constant times the state variable. And we're going to assume these are linear transitions. This is the rate out of I is linear. So we're going to assume that individuals are moving from the latency compartment or the exposed compartment into the actively infected or infectious compartment, also at a linear rate. Okay, so with this in mind, and you may notice that here there is not such thing as arrows going out and nothing coming in. We could add those things, but we don't have nothing like that right now. So this model is ignoring any demographic process. This model is neglecting, there is no arrows denoting death, natural death, and there is not an arrow here for newborns. Okay, we're explicitly concentrating here on the epidemiological process, the infection process. So the differential equation for S is minus beta times S times I over N. Here's the differential equation for the compartment of exposed individuals, right? You can see the gain appears as a positive term, and the arrow out appears here with a negative. The differential equation for I has the arrow coming in as positive, the arrow going out as negative, and then the differential equation for R has only one arrow coming in, so it only has one positive term. Okay, so it turns out that you can do experiments, numerical experiments with these equations. We still have the conservation of mass assumption, so we're assuming now the total population splits not just in 2 compartments, but in 4 compartments. And if you set values for the parameters and you use the solver that we've been using so far, we use LSOTA, then you can compute numerical solutions that look in this form. Okay, so here you have the numerical solutions that we obtain after choosing specific values. You need parameter values to compute this. You need parameter values. And you also need initial conditions. So you need values for beta. So what are the parameters here? The parameters are beta, kappa, gamma. That's it. Beta, kappa, the transmission rate beta. Kappa is the activation rate from exposed into infectious, and gamma is the recovery rate. Okay. You have values for those three parameters. Then you would need also initial conditions. Initial conditions are what is the number of S at 0, what is the number of E at time 0, what is the number of I at time 0, and what is the number of R times 0. This should be 0. Typically, both of those are 0. You just need numbers for what is the number, the initial number of susceptible, and what is the initial number of infectious. So for these simulations, we assume that beta has a value of 5, kappa has a value of 1, gamma has a value of 1, and then we made these assumptions for the initial conditions, okay? So you should immediately, you should rush off to the computer, open R or RStudio, and code up these equations using the solver LSOTA. And with these parameter values and these initial conditions, you should obtain numerical solutions that are very, very similar to the solutions we have here. So this concludes our discussion on compartmental models for basic compartmental models for infectious diseases.